We're now going to shift gears and go from the composition of compounds into the composition of solutions. And solutions are really important in chemistry because a lot of times chemicals will react better as solutions than they will in their solid phase or their liquid phase. And to understand solutions, we must talk about what's called molarity. So let's just first talk about what a solution is and then go from there. Now, in the real world, you don't have that many pure compounds. Usually things come in mixtures, all right? And a solution is a type of a mixture. It's an homogeneous mixture, which means you'll mix some things together and it looks like you have just one single phase. So as an example of that, let's say you took sugar, which is a solid, you can see it, and water, and you mixed them together to make a sugar solution. Well, it's homogeneous because it looks just like water still. It doesn't look like you have solid particles moving around or anything. So homogeneous mixture means that when you mix these things together, it looks like you have just one substance. But in reality, you have more than one. Now, if you mix these things well, and you always should, and it's usually not too hard to do, you'll have a uniform composition, all right, which means that the solution at the top will have the same values as the solution on the bottom. But to describe the composition, scientists will use the concentration term, and that's where molarity will kick in. Now, solutions do have two components. They're called the solvent and the solute. And the solvent is the component that physical state is preserved when you mix them together. So if you mix things with water, which is what we'll do most of the time in this class, the solvent phase, the liquid phase, is what the solution will look like. But the solute is really the more exciting part, all right? So that's the part that's usually present in a lower concentration, but this is why we're making this solution. So for example, hydrochloric acid is water plus HCl, but we don't call it a water solution, we call it a hydrochloric acid solution because the HCl is the exciting part. And earlier I talked about the sugar solution. Sugar is exciting, all right? You take a swig of that, you're like, whoa, you know it compared to water, right? It's that sweet, syrupy kind of sweet taste anyway. So the solute is the exciting part, the sugar in the sugar solution, but water is the component that actually is usually preserved as you go through. An aqueous solution is something where water is the solvent, and that's what we're going to focus on most of Chem 221 through Chem 223. And if you have an aqueous solution, it's going to get the symbol AQ, and I'll show you examples of that here in a little bit. So solutions, pretty cool, not only to us as human beings, but also to chemists. And if you see that AQ, that just means that water is your solvent. Now, molarity is a way to talk about how concentrated your solution is. So let's say you're making those sugar solutions and you put just a little bit of sugar in versus a lot of sugar in, and it's the same amount of water. Well, the little bit of sugar, when you taste it, will be sweet, but when you taste the one with lots of sugar, it'll be, you know, make your mouth power up. Anyway, my mouth is doing gymnastics right now. It's hard, you can't tell, but anyway, it's crazy. Anyway, the sugary sweet will have a really powerful taste, while the not a lot of sugar will be a lot less. So chemists will talk about these with molarity, and molarity is the moles of solute per liter of solution. And molarity is just a number. So like if you saw 3.6 m, that would be 3.6 molarity, which means 3.6 moles of solute in a liter of solution. So if you had a sugar solution that was 3.6 m, you'd have 3.6 moles of sugar in a liter of solution. But you could also have a 0.036 molar solution, and that would be 0.036 moles of sugar in a liter of solution. So that sugary sweet solution would be more like 3.6 m, and if you didn't have a lot of sugar, that would be possibly 0.036 m. So the number tells you how much solute is present. It's really helpful to chemists. This is by far the dominant concentration form. We'll talk about other concentration forms later, but you always have a solute. You add it to the solvent to make the solution. Water is usually our solvent, not always, but usually. Pretty chill. And now we can describe how much solute is in our solution, which is also cool too.
To prepare a solution of known concentration, we must first weigh the solute. We need an accurate volumetric flask designed to hold 250 milliliters. We first add the solute to the empty flask. The flask is filled about halfway with water and mixed to dissolve the solute. We add water in stages. Combining all the solvent with the undissolved solute in one step can lead to inaccurate measurements. We mix again. The solution is prepared.
This is the typical method that's used to create a solution. What they'll do is, first of all, you need to know how much solute you're adding to how much solvent. And in this case, they're adding 5 grams of nickel 2 chloride hexahydrate. This is a hydrated compound we talked about in chapter 3, no big deal. We're going to add that to enough water to make 250 milliliters of solution. And by the way, notice in the video how they measured from the bottom of the meniscus. So the meniscus is like the bottom of the curve of water. So chemists will usually measure the volume to the bottom right there, and that's the official way to do it. Now you want to make sure that all the solute dissolves, because unless the solute dissolves, you don't really have a solution. So they added about half the water, stirred it up so all the solid dissolved, and then they added the rest of the water so the bottom of that meniscus was right at that line. That's a 250 milliliter graduated cylinder, so that's a pretty accurate version of it. Anyway, let's say we make the solution perfectly. We can use this information to calculate molarity. So that big M is always moles of solute over liters of solution. So when this problem, to calculate molarity, we need to turn grams of the NiCl2.6H2O into moles. We also need to turn milliliters into liters. And by the way, 1,000 milliliters per liter will be a really helpful conversion for you on this, so make sure that you know it. So anyway, we'll find the molar mass of nickel 2 chloride hexahydrate. And when you do that, it's a nickel plus 2 Cls plus 6 waters. And when you do all that, 237.7 grams per mole. So 5 grams divided by the molar mass gives you the moles of the solute. We're also going to convert milliliters into liters. So 250 milliliters divided by 1,000 milliliters per liter is 0.250 liters. So the molarity, moles over liters, comes out to be 0.0841 molar, or that big M is what molar is. Sometimes you'll see it listed like this, where the solute is in square brackets, and it will equal then a number of molarity. Either way is great. You'll see it both ways. Now you're the hip chemist and can know what it is. So every liter of this solution would have 0.0841 moles of nickel 2 chloride hexahydrate. But you can see that we don't have a liter of solution. We have only 0.250 liters. So we'll talk about ways to extract the moles from the volume you add here in a little bit. In this example, we want to know what mass of oxalic acid, which is a compound you can get at the store or something like that. Oxalic acid has the formula H2C2O4. How much oxalic acid do we need to make 250 milliliters of a 0.0500 molar solution? So in this kind of problem, we know how much we need, how much volume we need, and we know the concentration, but we don't know how much of the solute to add to the volume to make that concentration. So it's an easy kind of problem to do. Molarity is moles over liters. So moles over liters times liters will give you moles. And that's what we're going to do on this problem. We're going to solve for the moles of oxalic acid that we need. That's going to be molarity times the volume in liters. And from the moles, you can find, using molar mass, you can find the grams of oxalic acid needed. Now remember, it's 1,000 milliliters per liter. So in this case, 250 milliliters is 0.250 liters. And if you multiply that by the big M is moles per liter. So the liters on top and the liters on the bottom cancel. 0.0125 moles of oxalic acid are needed. So if you had the molar mass of oxalic acid, which you can get from the periodic table, 2 hydrogens, 2 carbons, and 4 oxygens, that comes out to be 90.00 grams per mole. And if you multiply that by the moles you need, it turns out we need 1.13 grams of oxalic acid. If we add that to 250 milliliters of water, we'll have a 0.0500 molar solution. So this is kind of a cool way to make a solution if you know the concentration and the volume that you need.
To prepare our solution using the dilution method, we first obtain 2 milliliters of stock solution with a pipette. Filling the pipette with stock solution to the mark on the pipette ensures that we have 2 milliliters of this solution. We add the 2 milliliters of more concentrated solution to the 500 milliliter volumetric flask, touching the side of the flask with the pipette. We add water to the mark on the flask. After mixing thoroughly, we have exactly 500 milliliters of a solution with a concentration of 1.60 times 10 to the minus 4 moles per liter.
So when you're making a solution, oftentimes what chemists will do is they'll weigh out so much solid, find the mass, put it in so much volume to find the concentration, et cetera, which is no problem. And you can find how much solute you need, like we saw in the last example, if you know the volume and concentration. There's all different variations. But believe it or not, it's also very common to take a concentrated solution and add water to it to give a concentration which is less concentrated. A lot of the acids and bases that we use here at Mount Hood Community College come as very strong concentrations like HCl, sulfuric acid, sodium hydroxide. And what we'll do is we'll add water to it to make a solution which is more manageable. The pure acids and pure bases are so strong, they'll burn through things and do lots of things that we don't want to have happen, especially if it's like a lab where you're just beginning. So if you add water to it, you can then figure out what is going on. Now, when you add water to a system, the solution color usually changes. And so both in the video on the left and in these copper 2 solutions on the right, notice that as you add water, the color becomes less intense. So in the video, that orange became kind of a yellow. In the copper 2 solutions, the dark blue copper 2 became more dilute, like a lighter blue. And this is also very common. It's not all the time the case, but a lot of times you'll see that. So just keep that in the back of your mind. To figure out how much water you need to add, a lot of times chemists will use this expression, which is C1V1 equals C2V2. And there's lots of variations on this. So I used to use M1V1 equals M2V2. Sometimes you'll see MIVI equals MFVF. But the idea is that you have a certain concentration that you begin with and a certain volume. And you want to dilute the concentration to a new volume, V2. What is the new concentration C2 going to be? And you could do the same thing with M's and V's, whatever you want to. But the idea here is, remember that volume is usually in liters and concentration is moles per liter. So the moles that you begin with, the 1 values, equal the moles that you end with, the 2 values. So you're not changing the moles, you're just changing the concentration by adding or subtracting water, something like that. So let's look at an example. Let's say we had 0.850 liters of a 5.00 molar copper 2 nitrate solution, and we're going to place that in 1.80 liters through the addition of water. So the question is, what is our new molarity? All right. Now notice in this problem, we started with 0.850 liters and we ended with 1.80 liters. So that means you're going to add something like 0.95 liters of water. It's not that you're adding 1.80 liters to 0.850 liters. That's an important designation to make, and we'll talk about that here in a little bit. So in this question, we're just taking the 0.850 liters and adding enough water to make 1.80 liters. We can use this to find the new concentration. In this problem, 8.850 liters, that's V1. That's the initial volume. And C1 is 5.00 molar. So you can probably see then that 1.80 liters, that's going to be V2. We're going to solve for C2. So in this case, C2 will be C1 times V1 divided by V2. So it'll be 5.00 molar times 0.850 liters. We'll divide it by 1.80 liters. This comes out to be 0.236 molar. So our new solution is 2.36 moles per liter, which makes sense because we added more water, etc., etc. And again, note down there that we added 0.950 liters of water to make this happen. We didn't add an extra 1.80. We added 0.950 liters to make the old volume up to 1.80 liters. So here's a question you might see. We have 20 milliliters of 3 molar HCl, and this student apparently accidentally added it to 100 milliliters of water. So the total volume is 120 milliliters. What's the new concentration of HCl? And this kind of stuff happens intentionally and unintentionally. It's no big deal. But the good news is you can figure out what it is using that C1V1 equals C2V2. So in this question, C1 is 3.00 molar. Now, you could convert all of the volumes to liters, but as long as the volume units are the same, you can keep them in milliliters. So I'm going to use V1 as 20.0 milliliters and V2, the total volume, 120 milliliters. So it's going to be 3.00 times 20 divided by 120. And if you do that, you should get 0.500 moles per liter, answer D. So again, as long as the volume units are the same, you can keep them in milliliters. You don't have to go to liters. There's nothing wrong with going to liters, but why not make it